Yes, in the last lecture we were discussing about the relationship between potential energy and internal conservative force, and we saw that delta U being negative of integration of, or negative of work done by internal conservative force, or in differential form we can write this as, okay. So in a 1D situation, in a one-dimensional system, the internal conservative force has got only an x component, and the displacement also has only an x component. So this relationship becomes minus f dx or minus fx dx. So that internal conservative force itself becomes minus du by dx. So we saw this relationship that internal conservative force is negative gradient of potential energy. Okay, so let's begin with a question based on this relationship. Okay, so this was the relationship between force and potential energy. Okay, and then we'd also seen that if f is equal to 0 at a certain point, that means du by dx is equal to 0. So there is an equilibrium position at that point. So this is the condition for equilibrium. And further, if the potential energy has a local maxima, then the equilibrium is said to be unstable. Whereas if potential energy has a local minima, equilibrium is stable. So if we have a typical potential energy graph like this, let's say this is how the potential energy is varying. So now remember that when you look at the graph, the relationship between force and the graph of potential energy with respect to x, that relationship is that the force is negative of the slope. There's a local maxima here. There's a local minima at this point, x2. Okay. So now remember that force being negative of du by dx, that means in terms of graph, it is the negative of the slope of u versus x graph. Okay. So in this case, you can see what is happening in this graph. Force is before x1, if you see, the slope is positive. So the force is negative for x less than x1. And the force becomes in the positive direction for x between x1 and x2. Because here the slope is positive. If you see in any point like this, the slope is positive at a point like this. So this being negative of the slope, that means the force becomes negative. And here the slope is positive. Whereas in the second region, between x1 and x2, the slope is negative. That means the force is positive. So what does this positive mean? It's along the negative x-axis, or it's along the positive x-axis. So at a point like this, the direction of the force is along the negative x-axis. At a point like this, the direction of the force is along the positive x-axis, because the slope is negative, so the force is positive. Whereas at this point, at the equilibrium point, what is happening? The force is zero. So that is why you can see at x1 you have the unstable equilibrium, because the force on either side of it is pointing away from it. Whereas if you see at this point x2, again the force is zero, but beyond x2 the force is negative. So it points back towards this. Before it, it's positive, so it points back towards x2. So there is force which points towards the equilibrium position. So that is why it is the stable equilibrium position. So the force again becomes negative for x being greater than x2, because the slope in that region is again positive. So from that you can see what is also happening is that at x equal to x1, we have the unstable equilibrium. Okay. And at x equal to x2, we have the stable equilibrium. So this is something that we discussed in the last lecture. We'll do a question or two based on this today. Okay, so let's see another question based on this. So for a particle of mass 5 kilograms moving along the x-axis, it is 1D motion. Okay. Under the action of conservative force only. Okay. The potential energy is given by the relation okay, where potential energy is in joules and x is in meters. So first of all, find the position or positions of any equilibrium points. And secondly, which of these positions are stable or unstable equilibriums? Okay, so just start with this question. We will discuss. Oh, sorry, just make a correction here. This value is 10 and this value is 20. Okay, the equilibrium points are 1, 0, and -1. That all of you have got correct. But you're not getting the stable versus unstable as correct. Just try it again. See, for stable equilibrium point, you have to have a local minima. That means the derivative should be 0, and second derivative should be what? It should be positive. In local minima, second derivative is positive. In local maxima, second derivative is negative. Okay. So just check your result again for which of these points are stable and which of these points are unstable. Okay, so let me explain. See, for the first thing, now, obviously what you need to find out is at equilibrium points, okay, force should be zero. That means du by dx should be zero. Because remember, force is negative of du by dx. Okay, so that is negative of slope. Yes, Rahil, that is correct. Good. Rahil, your answer is correct. Good. Okay. So now u is given to us as this 5x to the power 4 minus 10x square minus 20. So du by dx is the derivative of this term. So as you know, differentiate the terms of 5 into x to the power 4. X to the power 4 will have the derivative of 4x cube. Okay. Then minus 10 into derivative of x square, that will be 2x. And then derivative of minus 20 is 0. So the derivative becomes how much? It becomes 20x cube minus 20x, or you can write that as 20x into x square minus 1 x plus 1. Okay, so this is your du by dx. So further you can see now that du by dx is equal to 0 implies that this term, that means x is 0 or x is 1 or x is minus 1. So these 3 points become our equilibrium points. Then next thing, at stable equilibrium, potential energy should have a local minima. That means du by dx should be 0 and second derivative should be negative. Sorry, should be positive. Okay. Whereas at unstable equilibrium, you should have a local maxima. So du by dx should be 0 and second derivative should be negative. Okay. So now let's just check up. Okay. So we have got derivative we saw was just now we saw it was 20x cube minus 20x. So second derivative is differentiation of this. Okay. So our second derivative is how much? It is 60x square minus 20. This is the second derivative term. Okay. So we will check the value of second derivative at these three equilibrium points. And if it happens to be positive, that means there is a local minima at that point. So there is a stable equilibrium. If it happens to be negative, then there's a local maxima at that point. So it is an unstable equilibrium. वरुण, for what we have to take negative sign? Force के लिए लेना है ना बेटा. But यहाँ पे तो we are finding out the local maxima and minima, na? So for that, why we have to take negative sign? Local maxima and minima of any function, how do we find out? By this concept that at the local minima, derivative is 0, second derivative is positive, and vice versa for the local maxima. If I want to calculate force at some point, then I obviously have to calculate the force. That is minus du by dx. That's fine. So the force at any point is this. It is minus of 20x cube minus 20x. That's fine. So it is 20x minus 20x cube. That is about the force. Okay, but I'm not calculating the value of force here. I'm just calculating where stable and unstable equilibrium is. So that is the position of local minima and the position of local maxima. So there's no additional negative term there, no? You understanding? Okay. Now, for example, if we add a part here, I'm coming back to this, but if we add a part that find the acceleration E at x equal to, let's say, 0.5 meters. Then for this, we'll first have to calculate the force at that point. So then, yes, we need the force from this formula. we'll calculate the value of minus du by dx at the point x equal to 0.5, and from that we'll get the value of force. Okay, but so far in this question, in the first two parts, we are just concerned with the equilibrium points, stable and unstable equilibrium points. So we have to accordingly calculate this. Okay, so now let's check out. So you got these values. So you can see that at x equal to 0, obviously du by dx is 0. And what about the second derivative? So put the value of x equal to 0 in this now. Second derivative is this. First derivative was this. So that is how much it is, minus 20. So that means we are having a local maxima. So that means the system has an unstable equilibrium. Okay. Whereas at x equal to 1, derivative is 0. And what about the second derivative? Put the value of x equal to 1 in this, it is positive, no? It's plus 40. So that means there is a local minima. Okay. So there is a stable equilibrium. Okay. We've already found out the equilibrium positions before in part 1. So we're using those values here to just check that which ones are stable and which ones are unstable. Okay, similarly, you will see that at x equal to minus 1, du by dx will be 0. But second derivative, again, if you put the value of minus 1 in the equation, you'll get it again as plus 40 only. So again, it's a local minima. So again, it's stable equilibrium. So finally, second part, what we understand is x equal to 0 is the unstable equilibrium position. And x equal to 1 and x equal to minus 1, they are both the stable equilibrium positions. Okay. So the value of potential energy which we are getting at x equal to 0, you will see it is minus 20 joules. And at x equal to 1 or minus 1, you will see it is minus 25 joules. So this is the minimum value. And this is the maxima. Local maxima, that is. Okay, so hope this is understood. Now let's come to the third part of the question. You have to find that if the kinetic energy of the particle is given to us to be 25 joules when it is at x equal to 0, then find the maximum possible kinetic energy. Okay. So we will apply conservation of mechanical energy. So third part, given that kinetic energy is equal to 25 joules at x equal to 0. So from this we want to find the maximum kinetic energy. Okay. So we can see that the sum of kinetic energy plus potential energy is the total mechanical energy of the particle, which is constant. So you can see that given at x equal to 0, the kinetic energy is 25 joules. That's just given here. And what about the potential energy? So potential energy at x equal to 0 is 5 into 0 to the power 4 minus 10 into 0 to the power 2, okay, minus 20. So the potential energy is minus 20 joules now. So the total mechanical energy is plus 25 minus 20. So that is plus 5 joules. Okay. So this is the total mechanical energy. Okay. Now, kinetic energy will be maximum when potential energy is minimum. And that will be at which position? At stable equilibrium. That is x equal to either plus 1 or minus 1. So from this now you find the maximum kinetic energy. Yes, that's correct. Okay. So we seen earlier that minimum potential energy was equal to minus 25 joules at x equal to plus 1 and x equal to minus 1. So this minimum potential energy plus the maximum kinetic energy should be equal to the total mechanical energy, which we've seen as 5 joules. So minus 25 plus is equal to 5. So maximum kinetic energy will be equal to 30 joules. And this will be the kinetic energy when x is equal to plus 1 or x is equal to minus 1 meters at these two positions. Okay, now finally let's come to the fourth part. So for the fourth part, the important thing is mass of the particle is 5 kg. Okay, potential energy is given to us, and we want to calculate the acceleration when it is at x equal to 0.5. So let's work this out. So we'll find the acceleration by using dynamics, that net force is equal to mass into acceleration. And the force is minus du by dx, which we saw was 20x minus 20x cube, like this. Okay. So at x equal to 0.5 meters, force will become 20 into 0.5 into 1 minus 0.5 square. So that is 10 into 1 minus 0.25. So 7.5 newtons with the plus sign. That means the force has a magnitude of 7.5 newtons and direction along positive x-axis. Therefore, the acceleration, so this is the answer. Okay, so hope this question is clear. Now we'll do some more revision questions. Okay, so we have a situation like this. Now particle is given an initial speed of v naught here, where this distance is d. Okay, so first part, given that d is equal to 10 meters, mu is equal to 0.2 meters, and h is equal to 20 meters. Find the minimum speed v naught such that the particle may reach the point E. Okay, and second, if v naught is equal to 50 meters per second, same values of mu d h as above, then find the particle's projection speed at A and speed at impact point on the ground below. So for this part, h prime is given to us as also 20 meters, and take g as 10 meters per second square. So try this out, people. Okay, so you can see in the first part, the condition for the particle to just reach A is that the kinetic energy at A should be greater than equal to 0. Okay, so for the particle to just about reach A, so if V naught is minimum value for the particle to reach the point A, then we can say that VA should be greater than equal to 0. Okay. So from initial point to A, the work done by friction should be equal to change in kinetic energy plus change in gravitational potential energy. So minus mu mg into d should be equal to half mva square minus half mv naught square plus mgh. Okay. So for va to be greater than equal to 0, it means that half mv naught square should be greater than equal to mgh plus mu mgd. That means v naught should be greater than equal to square root of 2g into h plus mu d. So minimum value of v naught should be equal to square root of 2g into h, which is 20, plus mu d, which is 2. Yeah, that's why. That's why the work done by friction we've considered as only minus mu mgd. No? In this part only friction is acting. And after this, there's no friction acting. There's only normal reaction and mg. Work done by normal reaction is 0. Mg is the internal conservative force. So work done by friction is only minus F into D. So minus mu mgd. Change this value to 25 meters per second for the second part now. Okay, so this you're getting V naught's minimum value is square root of 440 or approximately 21 meters per second. Yeah, survey see what is happening in the first part. As the particle is moving from this point P to, let's say, this point over here. Let's say this point is C. So P to C क्या हो रहा है? Work done by friction is equal to change in kinetic energy only. Okay, so minus mu mgd is equal to whatever that velocity at that point C is. Okay, like this. Then C to A, what is happening? The work done is zero because there's no friction, and work done by normal reaction is zero. So change in kinetic energy plus change in potential energy is zero. So half m va square minus half m vc square plus mgh is equal to zero. So if you now combine these two equations, this and this, to get the relationship between va and v naught at the point P, you will get the equation we have written below. This equation you will get. So for this full journey, what is happening? Work done by friction is equal to minus mu mgd. This is only from A to C, that part only. Whereas change in potential energy is plus mgh, and that is happening as it goes from C to A. So from P to C, initial point P to C. Zero mg is acting. I didn't understand, Sarvesh. Mg is not. Mg is the internal conservative force, na beta? So in the first part of the journey, it's moving horizontally. Na? So potential energy is not changing. P to C, okay, delta y is zero, na? So delta u is zero. And then C to A, the vertical displacement is plus h. So delta u is plus mgh. Mg is the internal conservative force, no? So here it is work done by external forces plus work done by non-conservative forces is change in kinetic energy plus change in gravitational potential energy. ये कुछ है नहीं, ये work done by friction है. Is it clear now? Okay. So you need at least 21 meters per second for it to reach the point A. Because otherwise it will stop somewhere before here and then slide back. Okay, now let's come to the second part. So obviously if we are giving a speed of 25 meters per second, it's going to reach the point A, and when it reaches the point A, it will have some non-zero speed, VA. Okay, so we'll just use work energy now. So we'll just use this equation only, this one. In this we'll substitute the value of V naught as 25, so we'll get the value of VA. So we need to find out VA. So work done by friction is change in kinetic energy plus change in gravitational potential energy. So minus mu mg d is equal to half m va square minus half m V naught square plus mgh. So from this you can see that Va square will be V naught square minus 2g into h plus mu t. Now when you calculate this, okay, so it will come out to be like this. Okay. Okay. And then okay, now that second part to find the VB, it's very simple. Yeah, very good. Sid. Okay. Okay, so hope this question is clear. Let's move on to the next one. So we'll do an example which has vertical circular motion next. Be a type of revision also for you of vertical circular motion concept. So this is a light thread suspended from the point O such that it can describe a circular path, vertical circular path with respect to O, with respect to the center at O. Okay. Now the length of the thread is given to us as 20 centimeters. Okay. And a particle of m equal to 2 kilograms is attached at the other end. Take g equal to 10 meters per second square. So the particle is given an initial speed v0 like this. We have to find if v0 is equal to 2 meters per second, then find the tension just after the particle starts with v0 and the maximum angular displacement. If v0 is equal to 2 root 2 meters per second, then will the particle complete the vertical circular motion? If not, then find the position at which the thread loses tension. So let's just do this as a revision question of application of work energy in work energy theorem in vertical circular motion. Okay, so what you can do here is now you can compare the standard values of V naught with root 2 GL. Okay, that is a typical important value. So that is how much? 2 meters per second. And root 5 GL is how much? That is root 10 or nearly 3.2 meters per second. Okay, so you know that for V naught less than root 2 GL, okay, it will behave like a pendulum. What will happen is at some angle of less than 90 degrees, V will become zero. It will go back and forth like this. Okay. You know that for V naught greater than root 2 GL but less than root 5 GL, the string becomes slack somewhere. Before it reaches, okay, so it does not complete vertical circular motion. Okay. Tension becomes zero at some point like this. And only for V naught greater than equal to root 5 GL, it completes the vertical circle. Okay. So when you're doing a vertical circular motion question, instead of directly solving, you can first check the values against these. So you can see that this value that is given, this is exactly equal to root 2 GL. Okay. So you can see that it will complete a maximum angular displacement of 90 degrees. I'll show it by the direct solving method also, but and this value is greater than root 2 GL but less than root 5 GL. So here what happens, it will not complete. The thread will slacken. So next let's come to the solving part. So you can see that at this point of time, if the tension is T naught, it's going in a circular path like this. This will be the tension. This is the dynamics of the circular motion. Okay. Whereas we'll also see that if the particle is somewhere here, where this angle is theta, okay, so if it stops at this position and this height is h, so the particle stops at theta equal to 90 degrees momentarily. So maximum angular displacement is 90 degrees. So this will behave like this. When you give it a speed v0 equal to that 2 meters per second, it will go from here up to the 90-degree position. And it will stop over there. Then it will come back by this path, have the velocity in the opposite direction. Again decelerate as it goes up. Again v equal to 0. So it keeps going back and forth between these positions. Okay, so hope this is clear. So the first part, when you give the speed of, ये तो the work energy से है ना, see, change in kinetic energy plus change in potential energy is 0. Here the kinetic energy is 0, the potential, acha, how we got h in terms of L, no? Okay. See, this is L, this is L. If this is theta, then you drop this perpendicular here. So now this is h, no? So this is how much now? This is L cos theta. So h you can see is L minus L cos theta. This is a standard thing in circular motion, vertical circular motion. You should know how to do this calculation of h in terms of theta. This is what you are asking, right? Is it clear now? Yeah, but see, it doesn't go above 90 degrees for V naught less than equal to root 2 GL. Na? So that's why we check that thing first. That root 2 GL का value कितना है यहाँ पे? यहाँ पे root 2 GL का value है this thing 2 meters per second. और root 5 GL का value है 3.2. So when it is 2 meters per second, it's not going to cross 90 degrees, because this is a condition for root 2 GL. And this is the condition for something greater than root 2 but less than root 5 GL. Okay. So second part now, that is where we'll assume that it crosses 90 degrees now, because second part, when we are taking the value of the initial speed as 2 root 2 meters per second, so that's approximately 2.8 meters per second. You can see that V0 is greater than root 2 GL but less than root 5 GL. Okay. So basically what will happen, the maximum angular displacement will be more than 90 degrees but less than, but it won't complete the vertical circular motion. Because tension will become zero at some theta. So now we want to find the position at which that thing happens. Now let's take this angle as theta. So actually the angular displacement will be 180 minus theta. Okay. So here if the tension is becoming zero, so let's say starting from the point A at B, if tension is equal to zero, it means that mg cos theta be equal to mv square by L, or v square is equal to GL cos theta. And secondly, A to B, change in kinetic energy plus change in gravitational potential energy is zero. This is our second equation. So here the height we're talking about is this total height. So it is L plus L cos theta. So that gives us the second equation here. So this equation and this equation, if we compare them now, we get this. Okay, so we can substitute this now. So L was 0.2, so GL is, so 2 cos theta is this. So you can see that the string will slacken when it undergoes an angular displacement okay. So at that point the tension becomes zero, the thread slackens. This is about 48 degrees approximately. Okay, so hope this question is clear, people. So this is a critical type of application of work energy for vertical circular motion. And I'm sure you've done the derivation of these conditions, for complete vertical circular motion, root 5 GL. For the tension to slacken, it's greater than root 2 GL but less than root 5 GL, and all these things. So make sure you revise that part and look at the application of work energy theorem here. Okay. So that's it for today's session, people. Wish you all the best. Next time we'll be starting with heat and thermodynamics. Okay. So we've now completed work by energy, including a bit of revision questions today. So next session we will start with the next part of physics, where we will move on from mechanics to heat and thermodynamics. Whereas in Hemant Sir's track, you're continuing with mechanics with the last couple of chapters. Okay. So that's it. Wish you all the best, people.